with formal languages using SML?
So this is my affiliation as an ML value, which strangely enough didn't end up on my badge. But most of this work was done when that was my affiliation. And next week I'm going to be moving to MIT Lincoln Lab. So I'm going to be talking about the Forlan project. And Forlan is a tool set for experimenting with the objects of formal language theory. Things like regular expressions, finite automata, context-free grammar is a universal programming language, and more. And it's implemented in standard ML as a library on top of standard ML of New Jersey. It's used interactively, but you can extend it via SML functions, and that's typically what one does. It currently consists of about 12,000 lines of SML code distributed over about 40 modules. There's also a Java application for creating and editing viewing finite automata. And the Forlan project also includes a draft textbook, and I've been trying to minimize the notational distance between the tool set and the book, and that's a huge goal for me in terms of pedagogy. So I chose SML as the implementation language for Forlan because, of course, its concepts and notation are similar to those of mathematics, but you can also write efficient code in ML. Efficiency isn't the top priority for Forlan, but it's an important priority. And my hope was it was going to be possible to naturally and simply express the definitions of formal language theory in SML and also implement the algorithms in ways that were simultaneously direct, natural, reasonably efficient. And so the talk is about how well this worked out. So, not surprisingly, I think my conclusions are largely positive. It was typically easy to naturally and efficiently implement the book's mathematics and SML, and I think both the core and module languages served well. And for example, most of the objects of formal language theory are naturally thought of as abstract types, and I implemented this using structures, signatures, and opaque description. And SML-NJ proved robust and provided sufficient speed. So the rest of the talk is going to be largely things that I didn't think were a perfect match. And first, some really trivial things, but that cause trouble in terms of pedagogy. There's no nat type. And natural numbers are basic in presenting formal language theory, and it's just annoying to have to constantly work with a bigger type. Along those lines, in SML-NJ as opposed to in Milton, as far as I know, there's no way of making int be the arbitrary precision integers. There is such a structure, but you can't say use it everywhere at the top level because I don't care that much about efficiency. And again, it's just an arbitrary thing to have to talk, an annoying thing to have to talk about. And then finally, along these lines, this kind of definition of functions over the natural numbers by structural recursion has to be turned into something that doesn't use a successor as a pattern. And these things all, they're friction. It's something that's not nice to have to talk about, explain to students. So to go a little bit deeper into this, these are the main types that Forlan provides. They're almost all abstract types. In fact, the only two exceptions are these ones over here. And in this diagram, the open arrows are conversions. The closed arrows are injection-projection pairs. So going up is essentially, well, an injection, and there's also a way of projecting down, raising an exception when that's not possible. And I'm just going to do a tour of this quickly. So working from left to right down the column. So the abstract type of symbols includes letters and digits and some other things that I don't need to tell you about here. Strings really are just lists of symbols, although there's a concrete syntax that's like what you'd see in a formal language book. Total orderings are this type here plus the usual axioms. And then built on top of total orderings, they're ordered sets, ordered finite sets. Second column, there's an abstract type of regular expressions. The third column is about different kinds of finite automata. and they're given meaning using labeled paths, and I'll show you an example of this later. But then if we work from top down, we've got finite automata where the transitions involve regular expressions, and then next down, there's strings on the transitions. Next down, there's strings of length at most 1. Then we've got NFAs where the strings have length exactly 1. And then finally, NFAs with determinism are the usual deterministic finite automata. And then there are context-free grammars, which are given meaning using parse trees. And then finally, the last column, I use functional programs for doing computability theory. And the closed functional programs, ones with no variables, are the ones that can actually be evaluated. So let me show you an example of what can be done with automata, and this will let me make some more complaints along the way. So this mathematical function here, all follow, takes in 2 strings, x and y, of zeros and ones, and it delivers a language over the alphabet 0, 1. And if you unpack this little set comprehension here, it's saying all strings of zeros and ones in which every occurrence of x is eventually followed by an occurrence of y, where there isn't necessarily a one-to-one correspondence between the x's and the y's that make them happy. And what I'd like to do is look at the problem of finding as a function of x and y a DFA with alphabet 0, 1 that accepts this language. And so you can do that in Forlan as follows, and we're going to put this code in the file examp.sml. So first off, they're built-in functions for converting a regular expression to an FA, and an FA, a finite automaton, to an EFA. We can compose them and go from reg to EFA. We can do a similar thing here to get a function from EFAs to DFAs. We can compose these two to get from regular expressions to DFAs. Min and rename, rin and ren, does DFA minimization, which produces state names that describe equivalence classes. And if we want to get rid of those and make the states be simple so that they're more efficient to work with and elide that information, we can do this renaming of the states at the end. So for instance, I can take the regular expression 0 plus 1 star, convert it to a DFA, minimize and rename it, and that's all string DFA. Of course, it's a single state DFA with transitions labeled 0, 1. It's an accepting state. If I want then to make this into an EFA, though, unfortunately, even though mathematically all string DFA is an EFA, I've got to do an explicit injection. And this is another one of these points of friction that in the book, I don't have to do that. It's just because I've defined things so that DFAs are NFAs, are EFAs, are FAs, but I have to do an explicit injection here. And then this last definition here, FA.FromString takes in a string and then makes an FA that accepts just that string. And then if we post-compose it with converting to an EFA, then we've got a function that takes in a string and returns an EFA accepting just that string. Continuing here, this function here takes in a string of zeros and ones, x, and it's supposed to produce an EFA that accepts all strings of zeros and ones that have x as a substring. And we can get that by doing the EFA concatenation operation, putting all string EFA at either end and string the EFA x in the middle. So accepting a string just if it's got x somewhere in the middle of that. We can get a DFA version of that by post-composing with this conversion to a DFA, and then we can minimize and rename. And then if we want the opposite of this, we can do complementation using the minus operation on DFAs. And so this function will take a string x of zeros and ones and give us a DFA accepting all strings that don't have x appearing anywhere as a substring. And, well, the complaint here is that the way I just described this, for this code to work, because these machines here are for the alphabet 0, 1, X better be a string of zeros and ones. If it has other symbols in it, it's not going to work. If we had dependent typing, then the type of this function could express that constraint. And in fact, it could also tell us that the resulting DFA that came, or EFA here, that came out would have alphabet 0, 1. But as we'll see, we're just going to have that information suppressed, and which means it will be possible to supply arguments that are nonsensical. And then finally, last slide of this code, sum not follow EFA xy takes in x and y, they're strings of zeros and ones, and it is supposed to return an EFA accepting all strings of zeros and ones in which there is an x, and after that there is a string that doesn't have y. So these are accepting strings that have an x, but that aren't satisfied, that there is no y that appears later on. This is the DFA version of that, and if we do complementation, now we have a way of creating a minimized DFA that accepts all strings of zeros and ones in which every x is eventually followed by a y. That was our goal. So complementations turn out to be really useful in solving these kinds of problems. So if we load this code in, then in fact we see that apparently we can just give arbitrary strings to these things. There's no way of reflecting that these better be 0, 1 strings. So that's my complaint about dependent types. Of course, I could have done checking, but I didn't want to have to do that. If we then use this as an example, we can call allFollowDFA with the string 0, 1. So this is loading a string in from its concrete syntax, and the string 1, 0. So DFA, assuming things are right, should accept exactly the strings of zeros and ones in which every 0, 1 is eventually followed by a 1, 0. The same 1, 0 can satisfy various 0, 1s, remember. And if we want, and it's displayed as an abstract type here, because we're not necessarily interested in seeing what it looks like. We may just want to do more operations on it. But we can visualize this by using this Java application called JForlan that my students mostly wrote. And so what we get is this kind of interesting little machine here. You can also see the concrete syntax for this DFA at the bottom in a notation that I think is pretty self-explanatory. So there's something kind of interesting going on in this machine, and we got it parametrically on the x and y, so you can work as many examples as you want of this allFollow function. If we want to test this thing, we can define a function accepted that tests whether a string is accepted by this DFA, a function find that tries to find a labeled path explaining why the string is accepted from the start state, why it's accepted by the machine. We're just specializing these functions from the DFA structure to our DFA. You might think that ending in a 1, 0 is enough to accept, but of course there's a 0, 1 right at the end of that string, which is why we get false in this case here. But on the other hand, ending here in 1, 1, 0 does work, and what comes back is a labeled path that's output to the standard output. That's the empty string, what it means, and you can see the explanation of how it worked out. So this gives you a little idea of the kinds of things that one can do, in particular that your students could do if you were using this in the context of a course. So then going on further with this, I talked about ordered sets, and here's a little bit of the signature for ordered sets. There's more, but we've got a type, a set, ordered finite sets, and then various operations on it. And let's focus on union down here. The idea is that every value of type a set is supposed to have a corresponding total ordering comp. And so union, you give it a first parameter, which is the total ordering, and then you give it two sets, which morally better correspond to that total ordering. And what comes out will be the union which will also correspond to that total ordering. So of course, this is another circumstance where if we had dependent typing, we could actually express that union takes in the comp, and then it takes in a pair of sets that are based on comp and returns a set based on comp.
Did you think about, so we have a similar issue with our actual set data type in OCaml, but I think it's the same story, where we basically just mint a fresh type to represent the comparison function. And then stash that in the set type. And so you have like, instead of an alpha set, you have an alpha called a beta set, where the alpha is the type of the element, and the beta is essentially a kind of existential type that's used for separating. And then the merge just demands that they're the same. The union operations. So I think you don't need to go so far as dependent types.
Okay. And maybe we could talk a few minutes afterwards about that. But in any event, the way this is done, in this simple-minded way, it's perfectly possible to mix things up inappropriately. So you can put two sets together that don't have the same comparison, or the comparison that's passed in as this helper might not be the right one for the set. So I've done a couple things as to mitigate. In the specs that I've written things like this, that if XS and YS are compatible with comp, then union XS YS returns the set that's compatible with comp and is the union of XS, spelled out like this. So as documentation, this explains what rules you have to follow when you build these things up. But these specs aren't, of course, even type checked and much less subjected to some kind of automatic verification. And I'll come back to that point. Also, most of the sets that are being used in Forlan are things on particular types where there's a standard comparison that one would normally use. And so what I've done is I've supplied various specializations of this. So sets of symbols, here's the specialized signature, which no longer talks about the total orderings. And then what we can do is take SimSet and use set and specialize it by calling it with the comparison argument in the first place. And note, of course, the value restriction causing a little bit of trouble for us here, having to do an ADA conversion there. So at least then using sets of symbols where you want the standard comparison, you're not in a position to easily not respect this requirement. Of course, you still could, because there's no reason why you can't use set directly. Okay, so back on this support for specifications. I'm frustrated that languages are not these days expected to have some kind of support for at least expressing specifications, both of correctness and termination. And long-standing gripe that SML doesn't even have convenient syntax for describing the type of a local function, that there's no good place to put it unless you want to say afterwards val f colon type equals f. You know, that's functionally equivalent to doing this. Other languages like Haskell have solved this problem a long time. If you use val rec, of course you can, but if you use the clausal form, there's no good place to put this information in. But making the programmer express correctness and termination specifications in an ad hoc syntax within comments means you can't even type check your specs, and that seems very old-fashioned to me at this point, that you go to all the trouble of writing these specs down and you don't even type check them. Ideally, though, I think a modern language should allow some kind of attempt at using an SMT solver or something like that to verify some of these automatically, or optionally let people use a proof assistant to assess validity. And heard a talk by Leno recently about Daphne, where he showed us in real time how well Daphne is doing with checking various specs. And I would really love to see someone take this up in the context of ML. So a minor thing is, because module structures are required to be not cyclic in their references. Sometimes it's hard to know where to put functions that involve the types from multiple structures. So, for instance, the RFA structure is concerned with converting FAs to regular expressions. It uses these regular expression finite automata as an intermediate language using this state ripping technique. These functions here all take in a regular expression simplifier as a helper, but you can see that this is going from an FA to an RFA. This is going from an RFA to a regular expression. So roughly, if you compose these two, you go from FAs to regular expressions. So this is like the top-level function that a user would use. It doesn't mention the RFA type anymore. We'd perhaps like to put it in the FA module or in the regular expression module, or maybe in both. It would cause no trouble semantically to do that. There's no actual recursion going on at the value level even. But we're not allowed to do that because that would create a dependency. And so this is kind of a trivial thing to complain about. We could create another level of structures where we fix that if we wanted to, but it would be nice to be able to do this directly. And then last thing, I mentioned subtyping earlier, and so let's think about the finite automata structure again. The FA structure has a concrete record with the data for a finite automaton. We've got states, start state, accepting states, and transitions, and I've just used symbols for states. They've got to be something, and we might as well use symbols because they're a denumerable set in Forlan. So a set of symbols and then a start state, which is a symbol. But of course, not every one of these records will be a finite automaton because this has got to be an element of that. This has to be a subset of that. All of the states appearing in here have to appear in the set of states. And so the abstract type of finite automata, what the user normally works with, has these two, is FA. It's actually a subset of this mathematically, the ones that meet these constraints. And then there's a projection from conc to FA and an injection going the other way around. This is just the identity. This is the identity when it's defined. It raises an exception when it's not. So that's okay, I think, so far. The abstract types of EFAs, NFAs, and DFAs are then implemented as increasingly restrictive subsets of finite automata as we go down toward determinism. And this is reflecting the fact that in the mathematics with this presentation, they're just inclusions. Every DFA is an NFA, is an EFA, is an FA. But because there's no way of expressing subtyping in ML, standard ML, you have to use explicit injection functions. Everything in all of these types, they're all at the top level abstract types. There's no way of doing this type relabeling without actually using an injection. And the EFA, NFA, and DFA structures have to unpack their values using these operations here. This is the way that I've defined this. So last real slide here. If we look at part of the DFA structure, it just implements DFAs as FAs. So from the DFA module's point of view, it doesn't, that's an abstract type. To do an injection from DFA to FA, it's just literally the identity. But to inject from DFA to, say, EFA, it injects to FAs, and then it has to project back down to EFAs. But that's never going to fail, because mathematically a DFA is an EFA. This is always going to be the identity, but this check here, the computation, won't be elided. That'll actually happen. There's no way of establishing sort of trust, some kind of trust between these different modules. And if we want to operate on a DFA in the DFA module, we have to first unpack it using fa.toConcrete, do a bunch of stuff, and then build a new concrete value, and then pack it back into the abstract type. So again, this operation here is going to do some checking. if the FA module trusted the DFA module, then that wouldn't be necessary. So to wind up, the summary is that for these reasons I mentioned before, things went really very well. So it's all working, but there's some things that nonetheless one might complain about in terms of how well Forlan was served by standard ML. And if you want to learn more about the Forlan project, that's the URL.